putting some numbers behind this, the dynamic range that the human eye can deal with is incredible. It ranges over 14 orders of magnitude. And there's almost nothing in the real world that works over 14 orders of magnitude, right? So that means 10 to the 14, 1 in 14 zeros times from the darkest dark to the brightest bright that you can deal with. And by the way, that does not include looking like directly at the sun, because frankly, you can't actually see much when you look directly at the sun. It's too bright, all right? But you can go from somewhere from 10 to the minus 6th to 10 to the 8th, what's called candelas, which is a unit of energy, per square meter. It's a measure of the amount of the flux of the light, and flux falls on a particular area. So the human eye can set its dynamic range, its set point, to anywhere from this really low, this 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, so that'd be a range of 2, up to 10 to the 6, 10 to the 7, 10, another range of 2. It can set it anywhere along that spectrum. At any given point in time, it's operating at least 100 to 1, maybe 1,000 to 1, maybe even more than that, depends upon how you're doing. And in any given sort of real world scene, like I was just showing you, the actual ratio of sort of the darkest area to the brightest area can sometimes be on the order of 100,000 to 1, right? So you're standing there, it's really bright outside, it's kind of dark in here, that difference might be 100. If it was that far, even your eye would have difficulty dealing with it. But it's way better than most imaging systems. Now the thing is, everybody knows about your pupil, right? When it's bright out, the pupil closes down. When it's light, when it's dark, the pupil opens up. That's a very small range of variation. A colleague of mine, the professor, actually used to say that it was like an order of 10 to 100 variation in terms of the size. He actually said 10, but I think it's a little smaller than that. But how do you do this great, huge variation? Well, it's actually the retina's ganglion cells that make this happen. And the way it does it is, and this is sort of looking at just a single section. So remember, light's coming in this way. Not too important for this thing. Here we have our photoreceptors. Here we have our horizontal cells, our bipolar cells, amacrine, and then there's these ganglion cells. But notice that this thing is referred to as the surround, the center, and the surround. And you can think of this as being a slice through a circular operator, okay? And that circular operator would look something like this, okay? In the retina, they're referred to as center surround receptive fields. And what that means is that, and the positive ones take the illumination that's from the middle, and they subtract off the illumination around the background. The negative ones do the negative in the middle and subtract and add the positive. But basically what they're doing is they're comparing the local illumination to a little patch of illumination to the overall illumination. So what happens when things get much brighter? Well, if it's just getting brighter over the whole thing, not a lot different changes. So one part of your retina can be sort of electrically and chemically setting its dynamic range at one place, and another part is at another place simultaneously. So the part that's looking at the bright window in the church is operating at one place. The part that's looking at the darker part, it's doing its center surround on a darker area, but it's looking at those relative contrasts. This plot here is just a notion of what a center surround field looks like.